In this video, we're going to start to look at the forces of friction. And when an object is in motion on a surface or through a viscous medium, there will be a resistance to this motion. And this is caused by interactions between the object and its environment. If you really want to get down to the root of the cause, it happens on a microscopic level with intermolecular bonds between two objects. We're not going to deal with that too much here, but we do want to understand how friction works on a macroscopic level. So how does it affect the overall motion of the object? And so we call the resistance that happens on an object that's in motion, whether it's in contact with the surface or if it's flying through a medium, which that could be air or that could be water, whatever it may be, this resistance to the motion is called friction. There's also another part of friction that resists the start of motion. So we can have friction even if there's no motion to begin with. And we will discuss these different types of friction in this video. A few notes about friction is that friction is proportional to the normal force. So the harder an object is being pressed into a surface, the more friction there will be. So typically this depends on the weight because the normal force is typically balancing the weight of an object. And so the more weight an object has, typically the more friction it'll have. That is not always the case, but typically that is the case. The force of static friction is generally greater than the force of kinetic friction, and we'll talk about the difference between these two types of friction in a moment. But the general rule is static friction is bigger than kinetic. The coefficient for friction, we use the Greek letter mu, depends on the surfaces in contact. So certain surfaces have more frictional properties than others, and that deals with the intermolecular forces. But like I said, we're not going to get into the microscopic level. We're just going to understand at a macroscopic level, sandpaper has more friction than ice. The direction of the frictional force is always opposite the direction of motion, and so that's either opposite the direction of the current motion or opposite the direction of the intended motion if we're dealing with static friction. And this last point seems possibly a little counterintuitive. The coefficients of friction are nearly independent of the area of contact. So the coefficients do not depend on the area that is in contact. Let's start off by talking about static friction. Now, first off, when we deal with friction, we usually use a lowercase f to signify friction. And keep in mind, it is a force and it is a vector. Now, if we want static friction, then we're going to have a subscript of s. And what is static friction? Well, static friction acts to keep an object from moving. So it wants to hold the object in place of where it is sitting at rest. Now, these next two statements are where static friction gets a little confusing. If we have a force applied on an object and the object is at rest, the object will have static friction, a friction that wants to oppose its motion. And so as we push on the object, as we increase the force on the object, the force of static friction also increases. And as the force decreases that we push, static friction also decreases. So it is a variable force. So it changes with the force applied, all to keep the object in equilibrium, because that's what static friction is trying to achieve. It's trying to inhibit motion. It's trying to keep the object in equilibrium. Now, there is a point where friction breaks down, and so static friction is always going to be less than or equal to the coefficient of static friction times the normal force. We want to keep this as an inequality to remind us that it is a variable force. It will change. It could be less than the coefficient times the normal force depending upon the force applied. If we know that there is impending motion, then we can use an equal sign. Once an object is in motion and is in contact with a surface, there is also friction going on, but this friction is called a kinetic friction, and we use little f sub k to signify kinetic friction. So say we're trying to push this trash can over here on the right. Once we apply a force big enough that it exceeds static friction, then the trash can break free and start to accelerate in the direction of the applied force. But as it is accelerating, there is also a frictional force inhibiting the motion in the opposite direction of the applied force and the opposite direction of the motion. Kinetic friction is not a variable force. It is a constant force in that it's constantly depending on just the coefficient of kinetic friction and the normal force. And keep in mind, the coefficient of kinetic friction is not the same between two surfaces as the coefficient of static friction. Typically, the coefficient of static friction is greater than the coefficient of kinetic. Technically, there are slight variations in the coefficient of kinetic friction when we operate at higher speeds. However, we are going to ignore these variations. Here's a table of a few different coefficients of both static and kinetic friction. And these tables are empirically derived. They're found through trials and trials and trials of experiments. And so there's no nice way to come up with these with an equation. It really deals with some high-level quantum mechanics when you want to try to figure out, well, what does the coefficient of static friction depend on when it's steel on steel? So we use these empirically derived coefficients for all of our equations, for all of our interactions, and they work pretty well. And so in looking at these, you can see that the static friction is bigger than the kinetic friction as we go down. Notice as we go down here, the highest coefficient of static friction between two surfaces is rubber on concrete, and that's a coefficient of 1, which is pretty good because that is what helps our cars to move, and that's what we're dealing with as we're driving down the road. We'll also notice that, hey, look, waxed wood on wet snow doesn't work very well. It doesn't have much friction, either static or kinetic. That's why we use waxed wood to, use on skis or snowboards or sleds to go sliding down a snow-covered hill. When dealing with objects that are on an inclined plane, we typically want to adjust our x and y axis and rotate them such that the x-axis is parallel with the inclined plane. And we see that our object has a gravitational force that is directed towards the center of the Earth, so we have a component of the gravitational force along our x-axis. So really what this does is it makes gravity break into components along the x and along the y. And so that imbalanced force in the x direction will cause the object to start to move down the inclined plane. However, there is static friction, and it's in the opposite direction of the impending motion. So if left to its own devices with no friction, the box would slide down the inclined plane. So there is kinetic friction acting in the opposite direction up the inclined plane. Now, if the x component of the gravity is big enough, then it can overtake static friction and start the slide. But if it's not big enough, then the static friction will be equal to the mg sine theta, and it'll be in equilibrium and just rest on the inclined plane. And so in these situations, it is key to make sure that we draw friction in the correct direction and know that it's going to oppose motion, and then apply Newton's laws and solve any equations for unknowns. Keep in mind, if the object is at rest, then we're dealing with static friction. If the object is moving, then we are dealing with kinetic. Let's say we have two objects that are connected with a rope. One object is on a table in a surface interaction, and the other object is just suspended in air. And they're connected with this rope, so the rope's going to have tension. And so we need to treat these two objects separately when we apply Newton's laws. So we have to look at the block that's on the table and look at what are the forces acting on that block. Well, that force has the normal force up, the force of gravity down, which as long as this isn't moving up and down, those are going to be balanced. And so the normal force is going to equal m1 times g. And then it also has a tension to the right and kinetic friction that is going to oppose it to the left. Now, this is assuming that we are in motion. If we are not in motion, then this kinetic friction just changes to static friction. And so we can find this tension based on the friction if we know the two surfaces in contact and we know the acceleration of the object. And from that, we can look at the hanging mass to see that, well, this hanging mass is going to have the force of gravity down and the force of tension up. And so the sum of these two forces is going to be the mass times acceleration of this object. One of the keys to remember is the tension in this object and these equations that come from this object is the same as the tension in this object. And you might argue that, well, in this tension we're going up and in this tension we're going to the right. That is correct, but these are two separate objects that those forces are the same, and we change directions based on the pulley. The simple machine of the pulley changes the direction of the force. Another way to approach connected objects, just like we had pictured in the last slide, is to treat the objects as one system. And this allows a quick check. However, it doesn't allow us to find much because we have to ignore all internal forces. And so tension would be considered an internal force. So tension would not come into play here. We would only look at external forces, and that would be like gravity and friction. So it doesn't tell you much about the system. However, it is a great check to see if it works with the acceleration of the system and the overall mass of the system. And so it can be used at times to do that quick check or to confirm answers. One final note and warning when dealing with friction, and I may have misled you a little bit in my terminology previously in this video. There is a distinct difference between kinetic friction and static friction. And at the surface you may say that it's just motion. If an object is in motion, then we're dealing with kinetic friction. If an object is stationary, we're dealing with static friction. Well, that's only partly true. It's more, are the surfaces that are in contact in motion, or are the surfaces that are in contact stationary? Are they not in motion? Are they resisting motion? And so where this comes to play is when we look at something like a car. As a car moves down the road, you might think, oh, well, it's moving, that's kinetic friction, when in actuality, it is the static friction that keeps a car on the road, and it's a static friction that propels the car down the road. That it's actually the force of the earth pushing back on the car from the car pushing on the earth that moves the car forward. Because really what's happening is as your engine turns and it transfers the force into the axle and starts to turn the wheels want to slide on the surface of the road or wherever it may be, whether it's asphalt, dirt, or some type of pavement. The tires want to slide, but static friction is keeping them from sliding. And so as long as you're not squealing your tires, you are using static friction to propel forward. And the direction of the friction, and this is what is kind of counterintuitive, the direction of the friction is in the direction of the motion of the car because it's resisting the intended motion of the tires to slide backwards. In addition to that, we do have a resistive force, a force resistive to the direction of the motion, and that is going to be air resistance, and that will be directed away from the direction of motion.